Hello, I'm Gianluca Marado and welcome to this new video. In data analysis, not all data points are created equal. Sometimes a few extreme values behave very differently from the rest of the dataset. These values are called outliers, and if we ignore them, they can seriously distort our analysis, change our averages, inflate variability, and ultimately lead us to wrong conclusions. In this video, I'll show you a simple and robust way to detect outliers using the IQR method, where IQR stands for Interquartile Range. It focuses on the middle part of your data so that extreme values don't dominate the picture. We'll start from a small numeric example, compute the quartile step by step, derive the IQR, and then use it to set objective thresholds that flag suspicious points, like the red ones you see on the chart. By the end, you'll know exactly how to apply the IQR method in your own analysis. On this slide, we focus on why outliers really matter. An outlier is simply a value that is much larger or much smaller than the rest of the data. Even if it's just one point, it can change our summary statistics a lot. Look at the bars on the right. Most of them are at similar heights. That's our typical data. Then we have that single very tall red bar, the extreme value. Notice the two average lines. The blue line shows the average when we ignore the extreme value. The red line shows the average when we include it. You can see how that one bar pulls the average upward, away from where most of the data actually are. The same happens with the standard deviation. One extreme point can make the data look much more variable than they really are. If we don't detect and understand outliers before building models or reporting results, we can easily draw misleading conclusions. That's why spotting outliers is a fundamental skill for every data analyst. Now that we know why outliers matter, let's introduce the IQR method at a high level. The idea is to focus on the heart of the data, the middle 50% of all values. On the right, you see a number line with a box in the center. That box represents this central half. Here's how it works in practice. First, we sort our data from the smallest value to the largest. This ordered list is the basis for everything that follows. Second, we find the two special points, Q1, the first quartile, and Q3, the third quartile. Q1 marks the boundary of the lowest 25%. Q3 marks the boundary of the highest 25%. The median sits in the middle of the box. Third, we look at the distance between Q1 and Q3, called the Interquartile Range, or IQR. It tells us how spread out the middle 50% of the data is. Finally, we use this IQR to define lower and upper bounds. Any value far beyond these whiskers can be flagged as a potential outlier. Step 1 in the IQR method is very simple but absolutely essential. We must sort data. On the top row, you see our small dataset in its original unsorted form. 30, 6, 9, 5, 7, 8, 6. The values are jumbled, and it's hard to immediately see how they relate to each other. The vertical arrow in the middle represents the sorting step. We now rearrange the exact same values from the smallest to the largest. On the bottom row, you see the sorted version, 5, 6, 6, 7, 8, 9, 30. Now the structure of the data is clear and each value has a precise position in the order. Notice how 30, highlighted on the right, looks quite far from the rest. It is visually suspicious, but at this stage we do not label it as an outlier yet. This is why sorting is so important. Quartiles, and therefore the IQR, are defined on order data. Without this order list, we cannot correctly find Q1, the median, and Q3 in the next step. Now that our data are sorted, we can identify the key quartiles. On the right, you see the order values, 5, 6, 6, 7, 8, 9, 30. First, we find the median. Because there are 7 values, the median is the one exactly in the middle, the fourth value, 7. This splits the dataset into a lower half and an upper half. The lower half is 5, 6, 6. The middle value of this lower half is 6. That value is Q1, the first quartile. The upper half is 8, 9, 30. The middle value of this upper half is 9. That value is Q3, the third quartile. So for this example, Q1 is 6, the median is 7, and Q3 is 9. The central 50% of the data lies between Q1 and Q3. In real projects, we normally don't compute quartiles by hand. We let software like Python, Pandas, or NumPy calculate Q1, the median, and Q3 automatically, especially when working with large datasets. Now that we have Q1 and Q3, we can use them to measure how spread out the central part of the data is. On the screen, you see the simple formula IQR equals Q3 minus Q1. For our example, Q3 is 9 and Q1 is 6, so the IQR is 9 minus 6, which gives 3. This single number summarizes how wide the middle 50% of the data is. Visually, focus on the highlighted band between Q1 and Q3 on the number line or box plot. All values inside this band belong to the central half of the dataset. An important point is that this measure depends only on that middle 50%. Extreme values, like our large value at the right, do not enter directly into the IQR calculation. That makes the IQR much less sensitive to outliers than the standard deviation, which is affected by every data point, including the extremes. Now we are ready to turn the IQR into concrete thresholds for outliers, using the classic 1.5 times IQR rule. On the slide you see the two formulas. Lower bound equals Q1 minus 1.5 times IQR. Upper bound equals Q3 plus 1.5 times IQR. Let's plug in our numbers. We found Q1 equals 6, Q3 equals 9, and the IQR equals 3. First, compute 1 point 5 times IQR. 1 5 times 3 equals 4. Now the lower bound, 6 minus 4.5 equals sine 1.5. And the upper bound, 9 plus 4.5 equals sine 13.5. On the number line, Q1 and Q3 mark the central region, while the lower bound at 1, 5 and the upper bound at 13.5 define the limits of normal values. Any data point below 1.5 or above 13.5 falls into the shaded outlier zones and is flagged as a potential outlier. Now that we have our lower and upper bounds, we can finally apply them to the actual data and flag the outliers. On the left you see our original sorted dataset 5, 6, 6, 7, 8, 9, 30. On the right we apply the limits we computed in the previous step. All values between 1.5 and 13.5 stay in blue because they fall inside the accepted range. The value 30 instead lies above the upper bound, so it is highlighted in red and clearly flagged as an outlier. In the box plot at the bottom, the box and whiskers span from Q1 to Q3 and out to the lower and upper bounds. Any point beyond these whiskers, like our red point on the right, is considered a potential outlier. This method works well in practice because it does not assume that the data follow a normal distribution. By focusing on quartiles and the middle 50%, it is robust for many real-world datasets with skewness or heavy tails. In real projects, detecting outliers is only the first step. Deciding what to do with them is just as important. An outlier is not automatically a bad data point. It might be a sensor error or a data entry mistake, but it could also be a real rare event, a market crash in finance, a sudden spike in sensor readings, or an unusually successful marketing campaign. Before removing any outlier, always ask what could be causing this value, and if possible, check with domain experts or additional data sources. On the screen, you see a simple Python example with pandas. With just a few lines of code, you can compute Q1, Q3, the IQR, derive the lower and upper bounds, and then filter your data feed to keep or inspect points inside or outside those limits. These techniques apply across many domains: financial time series, IoT sensor streams, web and product analytics, customer and marketing data, and more. The more carefully you handle outliers, the more trustworthy and reliable your analysis will be. Let's quickly recap what you've learned. You started from a raw dataset and sorted the values. From the ordered data, you identified Q1 and Q3. You then computed the interquartile range as the distance between Q3 and Q1. Using that IQR, you defined the lower and upper bounds, and finally flagged any points falling outside those bounds as potential outliers. With this workflow, you can now confidently detect outliers using the IQR method in your own analysis. If you want to practice statistics with real exercises in Python, download a free sample of my book, Statistics with Python, 100 Solve Exercises for Data Analysis. It contains step-by-step exercises on probability, hypothesis testing, correlation, and statistical analysis using Python. If you found this video useful, please like it, leave a comment with your questions or topics you'd like to see in the future, and subscribe to the channel for more content on data analysis, statistics, and real-world problem solving.